radioactivity, space physics. Alright, so in space physics, what we are supposed to do in our 6.1 according to the syllabus is this. That is, that we're not supposed to, we are supposed to have information about the Earth, what are the facts of the Earth, how does the orbital speed and orbital calculations take place. We'll also try to solve a numerical regarding that to understand how to use this equation. Let's move on to the next chapter. Okay, so again, this is all basic information that we know. So the Earth orbits around the Sun in 365 days. You're supposed to remember that. One day is exactly 24 hours, but there is a slight difference of approximately 3.5 minutes, or 3 minutes approximately. So that 3 minutes, when gets accumulated over the course of 4 years, that year we add one more day in February. That comes to be known as a leap year, right? Okay, so now we have the difference of day and night. If you were yourself standing on the North Pole, for example, right now, this student is standing at the North Pole, observing the South Pole, and on her left there is East, and on her right is West. So in winter season, she will see that the Sun actually follows this path. What is equinox? We'll get to that later. In the summers, it actually follows this path. Equinox would mean that right now the Earth is exactly at the same distance from the Sun as it is on the other side. And the reason we have to state this fact is because Earth's orbit is not exactly a circle. It's actually an ellipse. Let's go to that. So this is what the orbit actually looks like. It's actually an ellipse. So the point where the Earth has the same distance from the Sun on this orbit or this path is known as equinox. That is the only word, or that is the only fact that you're supposed to know. You're not supposed to memorize line of solstice or line of aspicites. We're not supposed to know that. But you must know or be familiar with this one. And the rest of the information is also not required. So what I am discussing with you is going to be according to the syllabus. You must remember the dates on which you find the equinox. You must remember what is the date when the Earth is the farthest from the Sun, and you must remember what is the day the Earth is closest to the Sun. Right? So these dates are a part of your, again, since it's my speculation, it's my understanding that they may be asking you these small little things because there's not a lot of information to think about from this chapter at least. We must know that this is an elliptical orbit or an ellipse orbit. This is what we must be familiar about that. And then the time for the light to reach Earth. You see, the distance between the Earth and the Sun is known. We know that distance. We know the speed of light in vacuum. So it takes approximately 500 seconds or approximately 8 minutes for the light from the Sun to reach the Earth. So technically, if we see the light that we receive on the Earth right now on this very instant is actually in the past. It happened 8 minutes ago. That is just a fancy way of saying that the light coming towards us is 8 minutes late, or it takes at least 8 minutes to reach us. Now the next thing according to syllabus, you will not find this in the syllabus, but I find this interesting in terms of at least understanding of the whole chapter. Why do we have seasons? Why do we have winter, summer, autumn and spring and so on and so forth? Why do we have them? You see, the Earth itself is actually tilted on its own axis. It's not exactly perpendicular like our own expression. For example, if I go towards the main map of the solar system, like this one approximately, okay, like this one. So to my eyes, it may look like that the Earth is actually perfectly straight. It actually has, or its axis is perfectly straight. But no, this is wrong. In reality, the axis is slightly tilted. And this is why we have seasons. This is why we have winter, summer, autumn, and spring. Now let's discuss in detail why is that so. Why do we see that happening with us? You see, when the Earth is tilted like it is tilted over here, let's divide the Earth in two parts. Let's say that there is a northern hemisphere and there is a southern hemisphere. You see, right now the southern hemisphere is a bit closer to the Earth, to the Sun, and the northern hemisphere is a bit farther away. So, whatever countries are actually closer to the northern hemisphere experience winter, and whatever countries are closer to the southern hemisphere under these circumstances in 21st December or approximately closer to the months closer to that experience summer because they are closer to the sun. Similarly, on the other side, we have spring, and because this actually is the stage of equinox for both sides. So the you can say that the season is pleasant for both hemispheres. It's not too hot, not too cold. Similarly, moving towards the other extreme, 21st June, right? And over here, even in this diagram, you will see that we are approximately over at this point. We are at closer to 3rd June right now, 3rd June. So it is June, July's month, the hottest, you can say, months of at least my country right now. So again, what's happening? That the countries that are actually on the northern hemisphere are now closer to the sun, and the countries a bit farther away from the sun are actually going to experience winter. So all of this has happened because of the tilt of the earth. So if the earth had not been tilted, probably we would have all the seasons to be the same, and the durations might have been the same. So but the one misconception that students have is that we experience heat from the sun because we are closer to the sun. Now, this diagram actually negates that myth. You see, January in Pakistan at least, January, February, and December, these months are cold. But in these months, we are actually on this side of the orbit, which is much closer to the sun. But in June, July, we experience the hottest climates, but we are at the farthest location from the sun. But then again, why is that so? So, not only is it due to the tilt of the earth, it is also because of one more reason, which we're going to study later, is that as you move away from the star, for example, in July, we are at the farthest distance from the earth, from the sun, right? The distance is the greatest. But in winters, the distance is very small. Not very small, but of course, in comparison to summers. So, what happens is that the speed of the earth reduces. So, at this location, the speed of the earth is low. Not the speed of its own rotation. It is rotating in 24 hours. But it's the speed at which it is completing the orbit is a bit less. So, it spends a longer time coming from this point and then going back to that point. It spends a longer time in this region, longer time. So apart from the tilt, we are spending longer time getting exposed from the sun, right? That hemisphere spends longer time getting exposed to the sun. But when we get to this side of the sun, when we are closer to the sun, in this region we spend less time, and the reason we spend less time is because the object, that is the earth, is moving faster. We are actually moving faster. That is why in Pakistan at least, we experience winter for a shorter duration and we experience summers for a longer duration. So not only that we spent less time in this location when the South Pole was getting exposed and the North Pole was away, so we had less time to experience winter, and the Southern Pole had less time to experience summers. So whatever is closer to the Southern Pole will always generally be found colder climatic countries, and in the Northern Hemisphere you will find generally hotter climatic countries. Generally, of course, right? And again, you'll need to research on this on your own, that whether this is the North Pole or this is the North Pole. I'm just telling you the theory or the idea behind it, but of course I'm not so sure right now that which one right now, the upper one is the North Pole, is the South Pole. Generally we do take the upper one as the North Pole, but for the sake of understanding, that will be your job. So you can explore it even further. So you can read this, right? I will be sharing the slide with you later on. You can read this and add the information. I would recommend not doing this from the slides, but doing this from the book, because the chapter, and I will share the PDF of the book as well. So the book has actually the complete picture, and you can make your own notes, and everything is going to be based on memory, every single thing about this chapter. So you can go and watch these videos, right, to understand why we have seasons and what are the phases of the moon. This is just extra information, not a part of the course, but just a bit to develop the understanding or at least interest in this chapter. This formula is compulsory for you for this chapter. So what he has done is told you about the radius orbital period, right? The average distance of the moon from the earth is this one. So if this is the earth and this is the moon, for example, then the distance between them is 380 into 10 raised to power 3 kilometers. So this is the orbit that it is actually trying to make. What he's asking you is that the time period is given to you as 27 days. It's going to take from this point, go towards that side, come back to this side, and take 27 days to do all of that. So what is the orbital velocity? Right, so simple, it's the circumference divided by the time taken. Simple mathematical expression to find the orbital speed, how long it's going to be in orbit and how long it's going to take to come back to the starting point. So you can do that. Then we have the solar system. We were talking about the Earth only in the previous case. Now we're going to talk about the whole solar system, right? And again, based on memory, so we have our star is the sun. We have 8 planets. Pluto is not a planet anymore. Keep that in mind. Minor planets include Pluto as a dwarf planet and asteroids. Dwarf planet, why do we call them dwarf, and why asteroids are considered planets but are not planets in true sense? Dwarf planets are those that they're so massive that they get squeezed under their own mass and eventually become a circle, eventually become a circular shaped, a round shaped object. Asteroids, on the other hand, they are massive objects but not high enough, so they have random shapes like this, right? So these objects will be referred as planets, but of course minor planets, one of them is dwarf and one of them is asteroids. Now, of course, we have definition of asteroids, then we have moons. Moons are going to be orbiting their respective planets, that is their quality. Comets are going to be, you can say they will be received from some other space, from other outer space, and they will try to enter our solar system. They will try to orbit it, and if their speed is so high or is very high, they might not even interact with any massive or gravitational object in the solar system and just pass right through it. For example, if this is our solar system, it's quite possible that a comet may actually move like this, navigating through the solar system and not colliding with anyone. But even if it, by chance, let's say, if it comes close to the sun, then it actually behaves in this manner, that it will be, it's like a slingshot. It will be slingshotted from the sun and then back to where it came from, right? Of course, it was trying to enter the circular orbit, but its speed was so high that it could not be catapulted back into the circular motion because of the sun's gravity, but because the speed was high. But that is how the probable or expected paths of the comets are going to be. So natural satellites, a new term, or at least a term for the moon already placed over there. We'll call them natural satellites as well. Now the sun, we discussed about this in the nuclear reactions as well. We have done this, that 99% of the mass of the solar system combined is actually concentrated in the sun. What does that mean? It means that if I were to place the sun on one side and place the rest of the solar system on the other side, this still has 99% mass of the whole system. So all the rest of the planets of my solar system only contribute to just 1% of the mass of my solar system. And wherever this pivots based on simple moments, that is known as the barycenter, right? Again, this is not in your syllabus. This is something that I've added as an extra information. Again, based on my, you can say, susceptance, or based on my own idea. So this is Necessity to understand, plus this is very important, Newton's law of gravitation. You will find this in A levels at the beginning of the second year of A levels, so I'm discussing it right now. You see, the law of gravity states that every massive object, doesn't matter what mass it has, it needs to have a mass. So every massive object in the universe is trying to attract the other mass that is close to its vicinity. So let's put it into perspective. You see, I am attracting the laptop that is in front of me. The laptop is attracting me because we are massive objects, right? The ballpoint that I'm holding right now is being attracted by the mass of my hand, and my hand is attracted towards the ballpoint. But why don't we see that happening in real life? Why? Because we are standing right now in the gravitational field of a much stronger or of a much massive object. So the Earth has a much massive or is more massive. So even these tiny gravitational fields between my hand, the ballpoint, the chair, the ground, the cabinets, the laptop, mobile phone, anything around you, you don't feel that happening in real life because you are present in the gravitational field of the Earth, which is much stronger than these tiny gravitational fields. But that does not mean that they don't exist. They exist, but we can't observe them because Earth is dominating in our case. Okay, so the force provides the necessary centripetal force to keep everything in our solar system orbiting the sun, and that we discussed this in the syllabus of ninth grade, or at least O1, the first year of O levels, right, or IGCSE. So we have already discussed this in the topic of circular motion, that why solar system is orbiting the way it is, because it doesn't only have the centripetal force, but the centripetal force is being provided by the gravitational force or attraction between the objects, right? So we must remember this point. Now we move on towards the planets. First we were discussing the sun, but now we move towards the planets. So the order of the planets must be remembered by you. You must remember the planets in their order. For example, let me give you the image again. Okay, so this one. You must remember that we start from Mercury and we end at Pluto. But remember, as I've told you before, that Pluto is not a planet anymore. We have rejected Pluto to be a planet anymore. So, since these images have been taken from the internet, I couldn't edit that out at that time, but I would just edit it out now. We will not accept Pluto as a planet. This is not a planet. But why is that so? Why have we rejected Pluto? You can search this online, that the reason we rejected Pluto to be considered as a planet is because it doesn't have those characteristics as a planet yet. So let's discuss that, although not a part of your course, but for your information. So we have some inner planets we call, we'll get to the Pluto point later. So the asteroid belt that we have right now, the planets that are on this side are known as the inner planets. And the outer ones on the other side are known as the outer planets. Right? Okay. So this is what we mean by the statement that we have made here. That there is a list of inner planets, a list of outer planets. Then what is the problem with Pluto? So we generally find that the inner planets are small, rocky, solid, multi-layered, warmer, and have higher density. Outer planets, Jupiter, Saturn, Uranus, and Neptune, they are large, colder, made of gas, low density. This is generally what's happening. So why is Pluto not considered a planet, and why only a dwarf planet? There is a strong enough mass to make itself a round object, so this qualifies as a planet. But what's the problem? But has not cleared its path of orbit by absorbing asteroid in its orbital belt. Its orbit is tilted in comparison to the other 8 planets, which does not make it a planet by definition. So the problem that we face right now is that if this is the Sun, all the orbits are like this. For example, like this, around the Sun. The orbit of Pluto is something like this. So it doesn't match with the rest of the rings. Its path doesn't match with the rings. Plus, it hasn't completed its journey, or even if it has not been able to absorb all the asteroids in its path so that it may have a clear path of rotation. So the only problem for us or for scientists not calling this a planet or the only, you can say, difference that we have with this planet is because it has still some asteroids or some of the path that needs to be cleared out so that we can definitively say that yes, this is the path of Pluto, but which it has not been able to do so far. All the other 8 have done so. You can read about this asteroids again based on memory, what they are made of. Extra information won't be required, of course, that one of the name of the asteroids is this, and this is what we will call them. This is what we don't call them. So that's not required. But we do need to know what is the difference between an asteroid and, of course, a dwarf planet, right? You can see that the asteroid is unable to maintain a round shape. It is a dwarf planet, but will be called an asteroid because it is not making a round shape. The Pluto will be considered as a dwarf planet because it can make a round shape. Again, moon of other planets as well. Then we have comets. This is what I was talking about, right? So comets, what are they made of, where they come from, that is going to be on your part. You're going to read this from the book based on memory and everything else. So this is interesting that I'm going to discuss. So orbit of the comet might come from the outer space. We don't know. There are some comets that are already orbiting the solar system that we already have, right? So when it does move very quickly, the gas that it is made out of starts to burn, and when it burns, we see a distinct trail behind it. This is its quality. This is the trail that we see behind it. So from sitting on the Earth, if I have just a general telescope, if I have something like that, I can easily identify that this is a comet, right? So what is this pattern that they are representing right now? So what happens is that when this actually comes closer to the Earth, this trail's pattern changes a bit. Although it's following a path like this, but its pattern changes. Why? Because it is getting some radiation, or a lot of radiation from the sun. So the radiation from the sun actually determines or puts pressure on this trail to be on the other side, right? So you can assume it like in this way, that the sun is blowing some wind, although there is no wind, but it's blowing a radiation pressure wind. You can search about this online. It's not part of the course. So radiation pressure. The sun has a lot of radiation pressure because it's very massive and very luminous. So it exerts a radiation pressure in all directions, which is why this lighting or this light trail fails to be on this side rather on the other side because of the pressure. Because it doesn't have that amount of energy to actually force its way to be on the other side. So looking at the trail of the comet, we can predict where the sun or where the star of that solar system might be. Because we know that if the trail is on this side, then the sun or the star should be on the opposite side. This is our guess. This is our estimate. Then we have natural satellites. You can go through that again. That is again based on memory. Overview of our solar system. We must remember these terms: inner, outer planets, where the asteroid belt starts. We have Mars before that. We have Jupiter after that. We are supposed to memorize it. Okay, so this slide is completely extra. This is extra information. Even the formulas, everything about this slide is extra information. You're not supposed to memorize it. But I'm going to discuss this in terms of law of gravitation and gravitational field strength. This is a part of your course, not the formula, but the concept. You see, this is the formula for gravitational attraction between two masses. M1 is mass 1, M2 is mass 2. So the sun can be taken as mass 1 and the earth can be taken as mass 2. R is the distance between their centers. So G is the gravitational constant. That is, you will find this in A levels, but I'm just giving you an idea that the gravitational attraction between these two planets is because of both planets. If we put in the values and we find out that the value of the force is, let's say, 500 newtons, although it's going to be very large, but let's say there is 500 newtons. What does that mean? It means that not only the sun is attracting the earth with a value of 500 newtons, the earth is also attracting the sun with a value of 500 newtons. This is the very essence of Newton's third law. Every action has a reaction, right? So if the sun is attracting the earth is also attracting the sun. And the nature of these forces is gravity. So by any point, by any definition, gravity is one of the Newton's third law, right? It's the nature of the force is same, the magnitude of the forces are same, they are opposite in direction represented by the arrows, which is the very essence of Newton's third law. Okay, so just a preemptive idea. So now we move on to gravitational field strength. You see, what does that mean? It means, in layman terms, in simple terms, if you are increasing your distance from the respective planet, how strongly is that planet going to pull you towards itself? You see, if you are at this point, or if you are at this point, or if you are at this point, and so on and so forth, you are moving away from the surface of the Earth. And in doing so, the gravitational attraction of the Earth is being reduced. Its grip or gravitational attraction on that level is reducing. So on the very surface of the Earth, we know that the value of gravitational attraction is 9.8. It's probable that at this point the value becomes 9.1. At this point it becomes 8.2. At this point it becomes 6.5. At this point it becomes 4.7 meters per second square. So the relationship that actually determines that is this one. What you are supposed to memorize is that gravitational attraction will be inversely proportional to r. And r is the distance from the center of the Earth or center of the planet up to the point that you're requiring to find out the value of g. So on the surface, we have the maximum value. If you start moving away from the planet, the gravitational attraction it can exert on that level will reduce. So from this mathematical expression, we find this. Alright, so gravity and planetary motion, we have discussed that, and this is the important part, that as the strength of sun's gravitational field decreases, why is it decreasing? Because if I consider the sun at this point, the Earth actually is at this location in June and July, and in this location in winters. So the Earth is actually following an elliptical path, right? So when it is further away, the value of g at this point is less. The value of g at this point is higher because it is closer to the sun. Because of this reason, mathematically, of course, we can justify this in A levels, but due to mathematically, what we find is that over here, the speed of the Earth is slow because the gravitational attraction is less. Over here, when they are closer to the massive object, the speed is high because they are being influenced, or they are under the influence of gravitational attraction of the sun, right? So then we have the next topic, and this is important in terms of ideas. We must remember this, that this results in a lower orbital speed and a longer orbital periods. So it's possible, for the sake of discussion, let's say we have 365 days around the sun. Let's say, for the sake of discussion, for an easier mathematical calculation, then let me split it down to 300 plus 65. Again, it's going to give me the same answer. So it's, again, just for the sake of understanding, I'm exaggerating the situation. This is not a fact. So since we are moving slowly in this region, we may be spending approximately 300 days on this side of the sun, because we're moving slowly. The length of path does play an effect, but still we are moving slowly. And within 65 days, we cover the other side of the sun. So even if it was a perfect circle and the length of path on both sides was the same, so if I increase the time simply from speed equal to distance over time, if I increase the time, that means that it must be moving at a slower speed because it has taken more time to cover the same distance. On the other hand, if I had set the same target for anyone to cover the same distance but in shorter time, of course they would start running faster to match the target. They will start doing more work to match the target. But over here, this is just an analogy to make you understand this, but over here, it is purely because of the gravitational attraction. Where it's high, you will see high speed. where it's low, you will see low speed. But of course, the gravitational attraction is not low enough that Earth exits the orbit or Earth roams around into the free space. It's not going to be like that, right? So that is all for today. From tomorrow, we're going to start with relationships from planetary data. We have this data from planets. What's their radius, what's their orbit time, what's their speed, surface temperatures, density, XYZ, so on and so forth. So you will also be given these values in the examination, right? And based on those values, what conclusions we are supposed to draw is going to be a part of your course, right? This is what we're going to discuss tomorrow, right? This is all for today. We'll start from this point tomorrow, inshallah.